This is the third video for week 9, and we continue our discussion on network clustering, and in particular we're going to look at our nested graph or hierarchical clustering. Now, clustering can be viewed as a method for data reduction. So we're going to see how clustering can be viewed as a way of reducing the amount of data. So let's suppose we have a very, very large network, and we can find graph theoretic values for each vertex, but that does not give us much information about the network's global structure. And conversely, we can find global values, but that loses information about local structure. So what we would like to do is come up with a way that we can preserve information at the local level and still reduce our amount of data by reducing the global picture. So what we're going to do then is to cluster the graph into highly connected subgraphs like we have been doing. But what we can do at that point is collapse each cluster to a single vertex. So if each cluster is approximately 20 vertices, we've replaced 20 vertices with one vertex. So we wind up with many fewer vertices. What happens to the edges? Well, the clusters that are now single vertices can be connected if there is at least one edge between the corresponding clusters. Now, I say at least one. You could set the threshold higher and require that there are at least 2 edges between the corresponding clusters, or however many edges you want. Now that you have a new graph, where each vertex represents a cluster in the graph, if it's still too large, you can repeat the process. That is, with your new graph, you can cluster and then reduce each cluster to a single vertex and connect correspondingly. So, for example, if you consider a graph where each vertex is an atom in the protein molecule, then you can base your clusters on functional similarity. You can base them on the three-dimensional distance, whatever is your criteria. But you can then reduce your protein graph by collapsing each cluster. So suppose that we take a protein and we cluster that protein molecule into 8 clusters. So that's what we have visualized on the right. G1, G2, G3 each represent a cluster, and G6 is illustrated, where each cluster, the vertices represent amino acids. And if 2 amino acids are in close proximity in the 3-dimensional structure of the molecule, then we have a connecting edge. But each amino acid in turn can be thought of as a cluster, a functional cluster. So if we start on the left, each of the 20 amino acid has a graph theoretic representation. Now think about its topology. So each amino acid has a different residue structure. So each amino acid can be represented by some graph theoretic measure or a list of graph theoretic measures. We can see leucine, which is represented by the letter L. And we could say it has maximum degree 3, domination number 2, diameter 4, and so forth. So associated with the amino acid L is a set of values. We can also include in those values some biochemical properties. It's hydrophobicity, polarity, and other aspects. So we have quite a few values we can assign that are unique to the amino acid L. So in the middle demonstration, where each amino acid is collapsed to a single vertex, we can assign a weight to that vertex that corresponds to the numerical values for L. We can do this for each one. So in the center, we have a graph whose whose vertices are amino acids, and those vertices have weights. Not a single weight, but rather an entire vector of weights. And in our setting, we'll call those weights attributes. So we can start over. We can take this domain structure and we can find graph theoretic values that incorporate those weights or those attributes. For example, if we want to find the longest path, rather than just counting the vertices we encounter along the path, we could add the weights as we go. Not all of them necessarily. We can pick out a subset of the weights, or we could add all of them and get the heaviest weighted path. This would be a good place to apply a greedy algorithm to get that. So the domain substructure can also be assigned a set of values that characterize it based on its structure and its attributes. So when we collapse again, we carry with it those attributes as vertex weights at the next level. So what we accomplish is we keep getting a smaller and smaller graph, something perhaps more manageable, and hopefully without losing too much information at the local level, because that information is contained in the attributes that were passed from level to level. So as we see, as I said in the previous slide, that the number of vertices is reduced, and therefore when we find at the last stage we can just find local levels, and it will tell us enough about its global topology. So here's a simple example. This is a network that you had in a previous homework exercise, and it's fairly easy to see that we have 3 clusters. So as a simple example, what we could say is we'll reduce each of the 3 clusters into a single vertex, and then we will connect the corresponding vertices if there exists an edge between those. So our graph that originally had 12 vertices has been reduced to 3, but we've maintained the overall or the global 3 cycle that we can see. And then properties about each of those clusters can be assigned to the vertices in the 3 cycle. So if we have a protein where each atom is represented by a vertex, it's easy to have a large enough protein that we would have tens of thousands of vertices, or at least more than 10,000 vertices. So we will treat each amino acid as a functional cluster and say on average each amino acid has 10 atoms. This would reduce our original representation of the protein molecule from, say, 10,000 vertices to 1,000 vertices. If in turn we now cluster this network, where each cluster has about 20 amino acids, then we would reduce our network down to 50 vertices. And as we said before, we can maintain some of the information at each level by assigning the weights to the vertices that correspond to the attributes of the cluster. So in summary for this week, not just this particular video, but all three, we have looked at an example of a graph algorithm method called the greedy algorithm, and we can use greedy algorithms to help us cluster our network. There are basically two methods for determining how to cluster, or two objectives that drive each method. One is we want to obtain high similarity within each cluster, and this is called cohesiveness. Or two, we want to obtain a certain number of clusters. We will have a number of clusters that we want determined a priori. So now that we've talked more about clustering, we see that we can use clustering as a method of data reduction.